and current flowing through this R1 as I1, okay, and the current flowing because of this resistance as II, okay. The input current that is rated input voltage is flowing to the input terminals of the op amp. That is, which are the input terminals, non-inverting and inverting terminal. And as you all know, like there is an invisible resistance that is always present in between the inverting and non-inverting terminal. And this is the input resistance of operational amplifier, which is existing between the two input terminals, non-inverting and inverting terminals. What is its value? Its value is very high. Already we've explained why the value of input resistance of op amp is very high. So you know that there exists a resistance between the non-inverting terminal and inverting terminal, and its value is okay found to be very high. That you have to keep that in mind. So now let us take the voltage, right? The same voltage here. So let us take a point here. Let us call this as Vg. Okay, right? Same thing here. So this is Vg, and let us call this voltage as Vb. Exactly, that is applied to okay inverting terminal. What is this Vb? So any voltage you know that is measured with respect to ground. Suppose if you want to measure the voltage at this point, that is always with respect to ground. Where is ground? Ground is here. So this Vb is always measured with respect to the ground that is found to be across the resistance R1. Okay, so this voltage drop across this R1 is appearing as the voltage that is applied to inverting terminal. Okay, so this is the resistance that is existing. Okay, and okay, and let us take, because we have to measure the voltage VB is always measured with respect to ground. Earlier, no, in the previous circuit, okay, the other terminal was grounded. So directly you could guess what is the potential at the other end, because already one terminal was grounded. Okay, as the resistance between the two input terminals is very high. Okay, so and hence the voltage at this point is should be obviously equal to the voltage at the other point. The voltage at the other point was known to you, it was grounded directly. Here you see it is not directly grounded. Okay, it is grounded through a resistance R1. Hence, you will have to find okay the voltage drop across this R1 to find what is the voltage that is present exactly at this point. I hope you are understanding. Earlier case, this was directly connected to ground. Okay, this point now it is not directly connected to ground. It is connected to ground through a resistance R1. Hence, if you want to find what is the exact voltage at this point, you will have to find the voltage drop across this resistance R1. I hope you have understood. Okay, and this resistance is, I mean, this voltage is, let us take this as Vg. Right. So now let us find out what is II, input current, right? So that is flowing through this. Okay, so now actually, so now you find out what is the voltage drop across this. So this is VB. Let us find the voltage drop across this. So if you want to find the voltage drop across this, so it is I1 VB is equal to drop across this resistance, that is equal to I1 into R1. So hence I1 is equal to VB divided by R1. I hope you are following. So we are finding what? The voltage drop across VB, right? So I mean voltage drop across this resistance R1. So that is found to be VB here, because we want to know what is the exact voltage that is applied to inverting terminal here. So how do we find it? This is the voltage drop across the resistance R1. So hence I1 into R1 gives us the value of VB here. So hence VB is equal to I1 into R1, or I1 is equal to VB divided by R1, or I1 is also equal to, I can write this as VG, or VG same as VI, right? So it is equal to VI, right, divided by what? R1. Okay. So now this VB can be equal to VI or what? This VB can be equal to VI or what? This VI is as VG only, this voltage is similar to VB or not? Can it be equated to VB? This VI, whatever that we are applying, can it be equated to VB? Can it be equated to VB, or can it be made equal to VB? Yes or no? Yes, or all of you with me? Hmm? Can I make this voltage at this point equal to VB? VB already we found what is VB. VB is equal to I1 into R1. Okay, so I'm asking you this voltage at this point, can it be same as this VB? Yes or no? I don't know whether you are hearing me or not. Respond me. Yes?
Yes, ma'am.
Somebody can answer. Yeah, can it be same? Can VG and VB can be same?
No, ma'am. No, ma'am.
No. Okay, then somebody else? Somebody else wanted to answer? Yes? No. Another no. Yes. Third. Third reply.
No,
We
ma'am.
have found VB, right? No. We have found VB. I am asking you, right, whether this VB, because in the previous case, no, the other terminal was directly connected to ground, and hence we took like this point and this point is same. If this is at ground potential, this is also at ground potential, correct? Is it not? This we know
Yes,
like
ma'am.
what was the voltage at the other end that was grounded in the previous case. So we took like this is also VG is also equal to VB. Right. This was grounded. The potential at this point was zero earlier. Okay. Now we know what is the potential at this point. This potential at this point is equal to I1 into R1. Okay. It is not directly connected to ground. Then I'm asking you whether this VB can be equal to VG. I mean, some of you told it is no. I say it is yes. It can be same. Why? In the previous circuit also we made like both the voltages are same. Why we made both the voltages are same?
Directly connected to ground.
No, it is directly connected to ground. See, this point was I told this connected to ground. Okay, right? We made this point this voltage equal to and this voltage equal to this voltage. Because we were not knowing what is the voltage at this point. So we knew like this point was connected to ground and hence we made this VG also equal to ground.
Your
What
voice
was
is
the
not
point?
clear.
What was the point in making that Vg is also at same potential? What was the main concept?
Gain.
What was the main concept for making both the voltages the same?
Differential gain exists.
Huh? Huh? Answer one by one. What was the main reason for making these 2 points, these two voltages the same? Whether it is
High
ground or something else, whatever it may be. Yeah. It is
potential between plus and minus, so high resistance will be there, no ma'am. Between A and
yeah,
B,
potential doesn't, yes, correct. Between A and B at this point and this point, there exists an infinite resistance which makes no flow of current. Current does not flow from this point to this point or from this point to this point. Okay,
so
right.
it
So when the current doesn't flow, when the current doesn't flow, what is the guess? Both the
voltage
ends must be, yeah, voltage levels must be same. Okay, so you know what is the voltage level at this point, at this exactly at this point. Okay, VB we know that is equal to I1 into R1. Hence, that should be equal to VG also because you know like between the terminals there is no current flow absolutely. So hence this point and this point should be at equipotential. Okay, so hence we can make I1 is equal to, so V1, I1 is equal to VB by R1 or VB is equal to VN or it is equal to okay. So VB is equal to VI that is equal to VG because VG and VB are same because okay there exists an infinite resistance between VG and VB. Okay, hence VG and VB has to be same because current does not flow whenever potentials are same. Okay, so hence this potential should be same as this potential, and because the resistance that is existing between these 2 points is very high, so current doesn't flow. When current doesn't flow means this potential and this potential must be at the same point. Then also the current doesn't flow. So because of this logic, this concept, okay, we arrive at a conclusion that VB will be equal to VI. Both the terminal voltages must be same because there is no absolutely current flow because of high resistance. So you keep this as it is. I1 is equal to VI divided by R1. So now what is actually we are intending to do now? We are going to find the voltage gain. Our aim is to find the expression for the voltage gain of non-inverting amplifier. Okay. So what is voltage gain? AV is equal to V naught divided by VI. Okay. Already we know what is VI. What is VI? VI is equal to I1 R1. What is that we need to find? We have to find V naught. What is V naught? Can any one of you tell me what is V naught? So to find the value V naught, so we need to find out what is the current flow because the voltage drop across this appears as the voltage output voltage at this point. Okay, so how to find the voltage gain? I mean output voltage expression. So now you see here this V naught, okay, minus this voltage, okay, right? So this V naught divided by the current that is flowing. What is the algebraic sum of the current that is flowing at this point? This is IF entering the junction. This current I1 is leaving the junction. This current, let me okay, take this because I was grounding this. What is this current? IG. IG is the current that is flowing to the exact input terminal of operational amplifier. Okay, so algebraic sum of the current at this point. Okay, IF is entering minus I1 is leaving and IG is also leaving. That must be equal to 0. I hope you have followed this. Current that is generated because of the output. Okay, IF is entering this point. Okay, IG is leaving the point and I1 is leaving the node. Okay, algebraic sum of the currents is equal to 0. Okay, right? So now IF, what can I take? IF is equal to I1 plus IG, or IF is equal to IG is 0, right? Okay, actual current that is flowing to the input is 0 because of high resistance, current doesn't flow. Okay, IG is equal to 0, IF is equal to I1. So what is IF here? Okay, so when no current flows through this, I hope you're following, IG is absolutely 0. Okay, so all the current, whatever that is coming as IF, okay, doesn't go towards the input terminal. All the current will flow through the resistance R1. Then we can assume that RF and R1 will be in series. Okay, so now the voltage, right? So V naught divided by R1 plus RF is equal to IF because IF and I1 are same. Okay, so the voltage, the current that is flowing through this will be equal to V naught divided by R1 plus RF. Okay, right? So now how do you find the voltage gain now? How do you find the voltage gain now? We got what is V naught. Okay, so what is V naught? V naught is equal to IF multiplied by R1 plus RF. Okay, so what is V1 or VI? That is equal to I1 into R1. Okay, so what is V naught by VI?
Voltage gain.
Voltage gain. Okay, so V naught by VI is equal to, so V naught, let me take IF multiplied by R1 plus RF divided by I1 multiplied by R1. So we have equated IF and I1 are same because the resistances are in series. Okay, so IF is equal to same as I1. So hence this will get cancelled. So you are getting R1 divided by RF divided by R1. So or else it is 1 plus RF divided by R1. Can we write like this? V naught by VI. What is that we are getting? RF plus or R1 plus RF divided by R1. If you separate this, no, 1 plus RF divided by R1. So this is the expression for voltage gain in non-inverting amplifier. I hope you have followed. What is, it's very simple. What is that we did? We found what is VI, because for calculating voltage gain expression, no, first you find, you think what is that actually you needed. What is that actually we needed? We need V naught divided by VI. So let us find VI, V1. Okay, RVI. What is that VI? The actual voltage that is applied at this point, VG. So to find VG, so we should know what is VB. So like we calculated VB, that is the voltage drop across the resistance R1. What is VB? That is equal to I1 into R1. Okay, so we found what is I1. I1 is equal to VB divided by R1. So as VB is same as VG, okay, that can also be equal to V1 or VI. Okay, so hence I1 is equal to V1 or VI divided by R1. So we got I1 here. Okay, so now coming back to what is other parameter we need? V naught. Okay, so what is V naught? Right. So here you will have to find the current IF. Okay, so V naught is equal to IF multiplied by I into R now, R1 plus RF. Okay, why they are in series? Because IG is not flowing to the input terminal, hence we consider R1 and RF are in series. So hence you can take V naught is equal to, okay, so that is IF multiplied by R1 plus RF. So hence V naught by Vi is gain. Okay. So hence gain is equal to this expression. I hope you have followed. Okay. So only thing is you have to find what is the value of V1 and what is the value of V naught. Okay. So you should know how to find the value of V1 and you should know how to find the value of V naught. So gain is V naught divided by Vi. So we are getting gain is equal to 1 plus RF divided by R1. That is the expression for voltage gain in non-inverting amplifier. So you can also notice that there is no sign change. Okay. So what does it indicate? There is no sign change. In the previous circuit, no, we got the sign minus RF by R1 we got. Okay, that shows that output is 180-degree out of phase with the input. If the input is going positive, output is going negative. If the input is going negative, output is going positive. Okay, so hence that works as inverting amplifier. So in this case, we are not going to get a sign change. It is plus. Okay, so plus 1 plus RF divided by R1. There is no sign change. That means output is in same phase with respect to input. There is no, okay, opposite polarity for the output. The output is not going to be inverted. So it is not inverted. Out in signal is not inverted. So it works as inverting amplifier. Right. So this is about non-inverting amplifier using operational amplifier. I hope you followed this. Almost all the circuits, no, we are applying same thing, finding the input current, finding the output current. Okay, in the previous circuit also we found the input current and we found the output current. In that way we are finding the input voltage as well as the output voltage. Our aim is only to get the expression for voltage gain or the expression for output voltage. Right. So next we shall study about differentiator circuit, op-amp as a differentiator. I will write the circuit diagram. See the components that are used here. Vi, let us say the current, this is the AC and this is the point VG and the current flowing to the actual terminal. Input is applied to inverting terminal and non-inverting terminal is grounded. And let us say this current is IG and this current is IF. Okay, This is op-amp plus VCC minus VCC biasing voltages, and this is our output. If op-amp is going to work as a differentiator, okay, what should be the output? Expression for output. Can any one of you tell me? Yes?
IF into RF.
No, if it is working as a differentiator, what we are expecting here? You are applying something here. You are applying something here. Right. What happened in inverting amplifier? If the input is applied, some input is applied here, output is inversion of the input. In non-inverting amplifier, output is non-inverted. I mean, it is not inverted at all. Okay, it is same as the input. You see the relationship between the output and input in both the cases. In the first case, output is inversion of the input. Okay. In the second case, output is not inverted. It is same as the input, of course, in the amplified version. Okay. If this circuit works as a differentiator, what is it we are expecting here? What should be the relationship between the output and input? What should be the relationship between the output and the input if it is working as a differentiator? Yes? V naught should be what? V naught should be proportional to d by dt of Vi. Correct? That is what we are expecting here. That means output should be differential of the input signal that we are applying here. That is the meaning of differentiator. It should differentiate. Okay. It should work as a derivative. Okay. So you know the meaning of differentiation or derivative. Okay. So it should work as a derivative of the input. Output should be derivative of the input, or it should be differential of the input. Then only we can say that op-amp is working as a differentiator. Okay, right. So suppose if I mean apply a sine wave here, what should be the output waveform?
Cos.
Very good. Okay, I hope you have understood. Right. So if I apply sine wave here, if the circuit is working as a differentiator, okay, so output should be derivative of the input or differential of the input, means if I apply a sine wave here, output should be cos. Okay, so that means it looks like sine wave only, but it is a phase difference will be there between the output and input. Then only we say it is working as a differentiator. Suppose if I apply square wave here, what should be the output? Can any one of you tell me? I am applying a square wave here. What is it I am going to get at the output? For sine, it is cos, derivative of sine is cos, you told. If I apply a square wave, because waveforms, no, they will appear in different shapes. So it may be a triangular waveform, or it may be a square waveform, or it may be sine waveform, right? Suppose if I apply a square waveform, okay, what can be the output? Can somebody tell me? See, simply I can tell you to take down the circuit. This is the input resistance, output resistance, this is the expression. So you should know like how actually the circuit works as a differentiator. Okay. So you should know the concept. You should understand the concept. Why do we say it works as a differentiator? So you know like if a sine wave is applied, it works as a, you will get a cos wave. Somebody is putting some message. Derivative of a square. You get a square? No, square wave means it is not square of the input, okay? Right. So do you mean to say that square wave means it is a square? Huh? Somebody is putting. Square wave area is, see here. Square wave is one which is the signal. It's constant from time period A to B, correct? And it's constant, okay, at the region C to D. Two different levels it has. It is a digital signal, okay. So, and its value is constant for certain duration. And also constant for certain duration. Of course, here it is negative and here it is positive. So it is positive constant between A and B. Signal is negative constant at between the duration C and D. That means it may be minus 5 volts, it may be plus 5 volts. That means signal is staying at plus 5 volts, okay, for the duration A to B. Signal is staying at minus 5 volts, I mean for the duration C and D. That means it remains constant. Okay, signal is remaining constant for the duration A and B. When you integrate this region, what is that you are going to get? Sorry, when you differentiate this region, what is that you are going to get? You are differentiating this region and you are differentiating this region because it's not a region at all. There is a sudden change. We don't treat it as a region. Okay. Square wave has only two regions, positive level and negative level. Both are constant. When you differentiate a constant, what is it you are going to get?
Zero.
0.
Exactly. You are getting 0. Correct. I hope you have understood. Okay. Signal is constant at positive level. Signal is constant at negative level. When we take a derivative of this, you will be getting a 0. That means to say, whenever we apply a square wave like this, see here, signal is trying to, I mean, increase, but suddenly it becomes 0. Signal is trying to increase at a negative level, but suddenly it becomes 0. That means you are going to get the spikes like this. Okay, you will not be getting any kind of signal at all. It is tending to become 0. It tries to increase, but suddenly you are applying a derivative, suddenly it becomes 0. So towards negative also it tries to increase, suddenly it sees like it is derivative, suddenly it approaches 0. Okay, you will be getting small spikes like this. Very small spikes you're getting. It doesn't look like a signal at all. Okay, so we call this as differential of the square wave. Almost the signal is almost 0. It is approaching 0. Okay, it is approaching 0. Right. So hence we say that output is differential of the input. Suppose if you apply a triangular waveform. Now we shall apply a triangular waveform. Like this. Now I am applying a triangular waveform like this. What I can expect here? What I can expect if I apply a square, I mean triangular waveform like this? Very good.
Zero.
No, 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 it is not 0. 0, like if your derivative of a constant is 0. Is it constant here? See here, it is not constant. It is a slope. It is a slope. It is also a slope and slope. You can see in the triangular waveform, positive slope and negative slope. It is a straight line. It's a first degree equation. Y is equal to mx plus c. If you derive a first degree equation like x, if you derive x, because it is a single degree equation, c is a constant, m is a constant there. It is an intercept c. Okay, so m is a constant there. Okay, x is a single degree equation. If you derive this x, what is it you're going to get? What is it you're going to get if you derive a single degree equation? What is derivative of x?
1.
1. It is a constant. It's a constant, right? So hence, for the positive slope equation, you are going to get a constant value. Okay. For the negative going slope, you will be getting another negative constant. So it repeats like this. For every positive going, you will be getting positive level. For every negative going slope, you will be getting another constant at negative level. As a result of this, you can see, okay, when you apply a triangular waveform to a differentiator, you will be getting a square wave. I hope you have understood this. So now you have understood, if you apply a sine wave, you will be getting a cos wave. Derivative of cos is sine is cos or cos is sine. Okay. So and if you apply a square wave form, because it is constant at some particular duration, derivative of constant is 0. Hence, you will be getting very narrow spikes. Okay. Voltage tends to become approaches 0. Okay. When you apply a triangular waveform like this, slope, I mean derivative of a slope is a constant. Hence, you will be getting two different constant level voltages. That is a square wave. So hence, so we one important thing that you can notice from this analysis is, okay, this circuit works as, okay, right, wave shaping circuit. If you apply one wave, you will be getting a different shape of the waveform. Okay, so hence the other important application of this circuit is it works as a wave shaping circuit. If you apply triangular, you will be getting square. If you apply square, you will be getting, I mean 0. Okay, like that, you will be changing the shape of the waveform. That is possible only in case of this differentiator and integrator circuits. Okay, so before explaining the analysis of the circuit, I wanted to tell you what is the importance of this circuit. So hence I told you what is the role of this differentiator for different kinds of signals. Okay, so now we shall analyze the circuit. For that, no, same thing. The algebraic sum of the currents leaving and entering the junction will be equal to 0 at this point, because we want to find, no, what is IC. Why we want to find the IC value? Because we need to know VI. Okay. So because gain is our output voltage, okay, is somewhere related to, or in some way it is related to input. It may be derivative of the input, or it may be inversion of the input, or it may be non-inversion of the input, or it may be integral of the input. So like that, some way output is proportional to the input. Now we have to find out what is the expression for output voltage in this circuit. Hence we need to know the expression for V naught. Hence we need to know the expression for Vi. For this we need to know what is the current at the input side and what is the current at the output side. So now for that, so we are finding out the algebraic sum of the current at this point is 0. So the current entering the node is IC minus, which is the current leaving, is IF. The other current is equal to 0. So as IC is equal to 0, IC is equal to IF. Okay, IC is equal to IF. So to find the current flow through the capacitance, okay, so how do we find the current flow through the capacitance? What is the current flow through the capacitance? We know that, so Q is equal to charge across the capacitor, because you know capacitor main property is to store the charges, C into V. C is the charges, okay, V is the voltage that is developed. Okay, so Q is equal to C into V. So what is IC? So IC is equal to the current flow through the capacitance, that is dQ, rate of flow of charges is current. Will you agree this? Rate of flow of charges is Q. Rate of flow of charge, rate means it is time. Okay, so rate of flow of charges is current. IC, current through the capacitance, is equal to dQ by dt. Okay, so what is Q? D, already you know what is Q. What is Q? Q is equal to C into V divided by dt. So take C outside. So it is dV by dt. What is V here? V can be taken as VI. So hence it is dVi divided by dt. What is that? IC. Okay. So that is the value of IC. So we found what is IC here. So then what is IF? What is IF? So IF is equal to, see here, this current, okay, resistance RF. Okay, so what is voltage here? Vg minus V naught divided by RF is the current flow through this resistance RF. Okay, so Vg is 0, right? So it is equal to minus V naught divided by RF. Okay, IF is equal to, right, so minus V naught divided by RF. So we already know, like by taking the algebraic currents at the junction, IC is equal to IF. So what is IC? So IC already we have found, C into dVi by dt. Okay, that's equal to minus V naught divided by RF. Okay, so now V naught is equal to, so take this outside, I mean this side, okay, minus C into RF d by dt of Vi. Okay, or you can take this, these two are constants, no? So it's directly proportional to derivative of the input. If you remove this constant, no? So it is Vi. Did you follow this? Should I have to repeat? Should I have to repeat?
Yes, ma'am.
Okay. See, this point is very important. To find the current, input current, so the main aim is to find the output voltage expression. Okay. So for that, no, we need to find the current. Current at the input side and the current at the output side. So for that, no, you find the algebraic sum of the current at this point is 0. We know that expression. Any doubt there? This expression, any doubt you have? Any
No,
doubt you
ma'am.
have in this expression? No, that's clear, no? So IC is the current that is entering the node, hence it is plus. Minus IF. IF is leaving the node, so it is minus. IJ is leaving the node, okay, it is minus. Algebraic sum of the currents is equal to 0. IJ is 0, you know. No current flows actual terminals of the op-amp. So hence IJ is 0 because of I resistance, IJ is 0, no current flows. So hence IC is equal to IF. This is very important. So now what we are finding? We want to find IC. How do you find IC? The current through the capacitance is our IC. Okay, how do you find the current through the capacitance? For that we need charges. Okay, so rate of flow of charges is current. Any doubt here at this point?
No, ma'am.
No, it's clear. Okay, so what did we do? We know the equation from PU classes, no? You know this equation. Q is equal to C into V. All of you know this, no?
Yes, ma'am.
Okay. So then what did we do? We found the current IC because we need the current IC. Input current and output current we need. That is all our aim. Okay. So we are finding the current through the capacitance. It is rate of flow of charges. So dq by dt is the current flow through the capacitance. Right. So we substituted CV in place of Q. Okay. So hence it is C. C we took it out. So dV by dt. What is V? V is Vi only. So hence C into dVi by dt, that is our input current IC. So here in this step now, we found the current through the capacitance, that is IC is equal to C into dVi by dt. Is it clear up to this point?
Yes, ma'am.
Okay. So now what is that we need to find? Output current. What is output current? Okay. The voltage drop across this is your output current. So what is the voltage drop? This voltage, this voltage divided by this resistance is the current IF. Okay. So hence we are finding IF is equal to this voltage Vg by potential difference across the resistance divided by resistance. Okay, potential difference is Vg minus V naught. Okay, Vg is 0. Hence we are left with minus V naught divided by Rf. So IF is equal to minus V naught divided by Rf. I hope it is clear here also.
Yes, ma'am.
Okay, so then we know that this expression IC is equal to IF. We know what is IC, we know what is IF now. Okay, equate both. Okay, IC is C into dVi by dt and that is equal to minus V naught by Rf. That is all we did. So you are going to find the expression for output voltage. That is equal to, these two are constants, no? Take it out. Okay, minus C into Rf multiplied by d by dt of Vi. So or otherwise, so it is directly proportional to derivative of the input voltage. The expression also shows that, okay, output voltage is derivative of the input. Hence we say that circuit works as a differentiator. Is it clear?
Yes, ma'am.
Is it clear now? Okay, because understanding, no, that's very important. So once you understand, easily you can follow the subject. Okay, so you cannot mug up all these things. So you have to understand. So if you understand it, you feel it is very interesting. So if you don't understand, you lose interest in the subject. Okay, so hence you have to understand the subject, you enjoy the subject. Otherwise, you don't feel like enjoying, okay, or listening to the class, right? So till you understand, so you can ask me. Okay, I don't mind repeating twice or thrice, but you should be able to understand the things. I hope you have understood differentiator and non-inverting amplifier.
Yes, ma'am. Yes, ma'am.
Okay. If anybody has any doubt, you can ask me. I mean, among these two circuits. I assume no doubts. Hmm? Only and 75 students or 74 students are attending. What about remaining students? Where are they? Huh? Ma'am, notes. Okay, you are very much fond of notes. Huh? First, you have to listen to the class. Okay, notes, no, like once you go through, if you understand and if you go through, because in notes, no, I have elaborated the things and written the notes. Only the purpose is to make you, because it's online class, I have given more description in the notes. That need not be written while you write the answer. Okay, you read the notes and you write in your own sentences. Okay, I have also written in my own sentences only. Okay, you also read the notes, understand, and write in your own sentences. Doesn't matter. Okay, circuit should be correct, equation should be correct. Sentences can be of your own. Okay, right? So I'll give you. Today evening I think I'll give you. Why you are so much fond of notes? Test is approaching. Because of the test.
Yes, ma'am.
No, you should not always study the things because of test or examination. Okay, so you should always study the subject with the interest to know and understand the things and concepts. Then obviously you will marks will follow you. Okay, definitely the marks will be behind you only if you understand the subject. Okay, so for try to understand the concepts properly. Other things definitely will follow you, right? I'll be giving the notes today because it is incompleted. Yesterday I could not complete. I think regulator, I think I'm writing right now. Okay, amplifier already written. Okay, this is already there from your seniors. You can collect the notes. Once again, I'll be giving to you only. Okay, so evening I'll give you. So I think I hope you have followed the two circuits analysis, right? So let us conclude the class, right? Any no more doubts? I think so. Okay, thank you all.